Welcome everyone to another webinar on evolution equations and dynamical systems. Today is my pleasure to present Professor Oleksiy Kapustyan from Taras Shevchenko National University of Kyiv. I don't know if it's, I don't know, I spoke right.
Yes, you're right.
Today, Professor Oleksiy Kapustyan will talk about attractors for infinite dimensional impulsive systems. Thank you very much, Professor.
So, hello everybody, colleagues. Greetings from Ukraine, from Kyiv. I'd like to thank organizers for invitation and this opportunity to present some recent results concerning uniformly attracting sets for infinite dimensional impulsive dynamical systems. So, brief outline of my presentation. First, we will speak about classical or continuous theory of global attractors, dissipative infinite dimensional dynamical systems. So I concern classical results about existence, invariance, stability, structure, and robustness. And after that, we consider some general constructions concerning impulsive dynamical system, infinite dimensional. And so it will be general construction plus I introduce the notion of attractor for such systems, explain why we choose some definition and this definition and give some existence and non-existence results trivial. After that, we will go to nonlinear case, to impulsive dynamical system for nonlinear PDEs, existence. We will consider existence, invariance, with application to weakly nonlinear parabolic equation with impulsive perturbations. The next step is stability properties. I again introduce somehow new concept of stability for impulsive systems and give abstract results and application to parabolic problem. And in conclusion section, I present some other results. So parabolic systems, hyperbolic equation with impulsive effects, and also some new results, non-published results as an application. So let's start. The classical theory of global attractors. So we have autonomous problem 1. His is differential operator, I have some nonlinear term, and H is infinite dimensional phase space. And I assume that for every initial data U0 from H, we have globally defined to solution in some sense, in weak sense, in mild sense, it doesn't matter. So then we have classical dynamical system, classical or continuous dynamical system V, according to the rule 3. And if we are interested in a limit behavior of trajectory, we should consider omega limit set of particular point, yes, U0. But if we're interested in a global limit behavior of this system, we need a slightly more wide object called global attractor. So global attractor is a compact set, theta, from the phase space H, which is invariant and which is uniformly attracting. So theta attracts all bounded subsets of the phase space. Dist here and after dist means Hausdorff semi-distance. And a global attractor, if it exists, is the minimal among all uniformly attracting sets. So the main questions in this classical theory is, first of all, of course, existence, because existence in infinite dimensional case it's not simple. It's not a simple problem because it's not a direct consequence of dissipativity. So existence, stability of global attractors in usual Lyapunov sense, structure and regularity of global attractor. It's important questions, and finally, robustness of global attractor. This is, of course, not complete list of questions concerning attractor, but this list will be important for this presentation. So, existence theory, the classical result, if our dynamical system V is continuous with respect to initial data, dissipative, so we have a bounded absorbing set in the phase space, and asymptotically compact, so limit behavior of our system should be compact in some sense. Then this set theta is omega limit set of B0. B0 is a set of dissipativity, gives us a global attractor of this system. It's unique, independently on B0. This is the unique set. If it exists, it's unique. The next step is, of course, the global attractor. If our phase space is the Banach space or Hilbert space, then the global attractor is connected according to definition. It can be proved. And this is the classical Lyapunov stability definition of compact invariant set. And if we additionally assume that our function V, our dynamical system, is continuous with respect to both variables, then our global attractor will be stable in this sense. The next one is about structure. If we introduce the notion of complete trajectory, then again, according to definition of global attractor, the global attractor consists of bounded complete trajectories. And I want to emphasize that this property, this structural theorem 1, is a consequence of invariance. So if we have invariant compact object, then it consists of bounded complete trajectories. Nothing more. So this theorem is a direct consequence of invariance. If we have additional information about, for example, stationary points, if we introduce unstable sets as a set of points lying on complete trajectories which emanating from this stationary point set, then in the presence of a Lyapunov function, our global attractor will be gradient. So it will have gradient structure in the sense of this equality 7. If this set of stationary points is discrete, then the structure of global attractor is completely understandable. So it consists of stationary points and complete trajectory we join these points. And the final classical result is dependence on parameter. As a rule, this question appears if our right-hand part of our equation depends continuously on some parameters. So if we have a collection of dynamical system V lambda some parameter, and near some non-isolated point lambda 0, this collection of dynamical system is uniformly dissipative. So there is a point, there is a set B0 which is dissipative for all these systems, which is an absorbing set for all these systems. And this is the first assumption. The second one, this function v lambda must be continuous with respect to both variable lambda and x. And the third one is the uniform asymptotically compactness of this family v lambda. If these conditions take place, then our global attractor theta lambda upper semi-continuously depends on this parameter. So this theta lambda 0 tends to 0 as lambda tends to lambda d. I want to present some application how it of course this result is also classic, but I will use this nonlinear problem as a test problem for impulsive case. So let's speak briefly about application to reaction diffusion system. So we have this parabolic problem, and in bounded domain, F satisfies some sine and Gauss assumptions 10, classical, for example, polynomial F with positive leading coefficients, and assume also that the derivative of F is bounded from above, but its assumption is technical. For example, Chaffee-Infante equation satisfy all these inequalities. So the solution we will understand here and after in weak sense. So in the sense of this integral equality, and here and norm and scalar product in all this presentation will be the norm and scalar product in phase space L2. It's known that for every U0 from this page H, there exists a unique solution of this problem starting from U0. It's a continuous function, and all these solutions generates a continuous dynamical system V, infinite dimensional. So this dynamical system is defined on this phase space H, and here is the conditions how we can verify the existence and properties of global attractor. Here is the continuity. After that, dissipativity is a consequence of a priori estimate in the phase space. Asymptotic compactness in parabolic case, in this particular parabolic case, is a consequence of this estimate in the space H01, which is compactly embedded in the phase space H. So, and the regularity we can obtain from this Lyapunov function. This function is well defined on this subspace H01 intersect H2, and so our attractor belongs to this subspace, so no problem. We have Lyapunov function on the attractor. So having in hand these properties, we can prove this result. So a dynamical system V generated by our problem possesses connected stable global attractor, which is compact in H2, bounded in L infinity. So it consists of bounded functions, smooth bounded functions, and it attracts all bounded subsets from L2 in the stronger topology, in the topology of H01, and it has gradient structure. And additionally, if the right-hand part Fn tends to F uniformly on the bounded intervals, then the global attractor also converges to global attractor of unperturbed system. Is dependence on parameter. In this presentation, I restrict only single valued case, so classical case, when we have uniqueness of solution. But all results will be valid for multi-valued case, so if we have no uniqueness of solution. The next result is rather fresh. His also can be considered as a robustness result. Assume that our problem is perturbed by some non-autonomous signals d of tx. D of tx is a bounded function, bounded external signal in the system. So our system is no longer autonomous, and the main question is the estimate the deviation between trajectories of this perturbed system and the global attractor of unperturbed one. And we can do it within the theory of input to state stability. If we denote by Vd TU0 solution of this problem starting from U0 and introduce the set of strictly increasing function gamma, continuous strictly increasing functions, which is vanishing at the origin, then the following results takes place. There exists some function gamma from this class K that for every initial value 0 and any external bounded signal D, upper limit of this deviation, so norm of theta means the distance between x and theta. So upper limit of this norm less than gamma of D infinity. So it's a rather fresh result. This is about robustness of the global attractor in classical continuous case. A few words about problems which are beyond the methods of classical theory. This is the first one. This is the evolution system with time-dependent coefficients. And in this class, we can include the evolution system with impulsive effects at the fixed moment of time. This problem is non-autonomous. But here is a lack of semi-group property, but there is another good object for describing these problems. This is the semi-process theory. And for this semi-process theory, we can introduce the notion of uniform attractor and obtain almost the same results. Because what we need here is a continuous dependence on initial data and on these non-autonomous parameters. If we have such continuous dependence theorem, we can adopt to the situation all constructions from the classical theory. No problem. The next problems. This is evolution inclusions and equations without uniqueness. Like inclusions, so the evolution object with multivalued right-hand part, or just an equation with non-smooth interaction functions, for which we cannot prove uniqueness, or we can prove that uniqueness is failed. So in any case, here is a lack of uniqueness property, but we can use the multivalued approach. And in this multivalued approach, the key moment is the upper continuous dependence of the set of solutions on initial data. Instead of continuous dependence, we have upper semi-continuous dependence for some multivalued mapping. And in any cases, we can obtain almost the same results again as in classical theory. For example, just a few seconds, if we assume only conditions 10 without conditions 11. So we have no uniqueness, but this theorem will be true. Just with slight additional assumptions on parameter connecting dimension of omega, something like that. So this is not the problem. And the third one is the evolution impulsive system. And here we face with real problem because lack of continuity property is a serious problem. These systems have no continuous dependence on initial data in any sense. So this is the subject of my today's presentation, and I want to show how the theory of attracting sets borrowed from the first one, from the theory of non-autonomous system, successfully works at this case. So, impulsive dynamical system, what we understand, what does it mean, impulsive dynamical system? So, this is the evolutionary problem, autonomous evolutionary problem. And M is some closed set from the phase space H called impulsive set. I acting on M called impulsive map. And the evolution of this problem consists of continuous behavior, but if the phase point reaches the set M, it jumps in a new position, I of M. And after that, again, we have continuous dynamic till the next intersection, etc. So assume just for now, assume that we know that for every initial data U0 from H, there exists a globally defined right continuous is just it's for convenience, right continuous solution of this problem. The main difficulties are this map is not continuous. We have no continuous dependence on initial data. And so the omega limit set is not invariant. This is the real problem. And moreover, the omega limit set depends on this parameter M and I. So the result of classical dynamical system theory cannot be applied. In fact, directly, we need to overcome these difficulties. The dynamic may be unusual even in the simplest case. So let's look at this picture. So we have the real planar dynamical system. The point 0 is a focus, stable focus. And M, the impulsive set, is a circle of radius R1. And if we reach this circle, we jump into a new position on the circle of radius R2. And again, and again, and again. So it jumps along the radius. And it can be proved that if this number is not rational, that for every U0, the omega limit set is the whole disk. So it's completely unusual from the point of classical dynamical system theory. So of course, we can expect unusual behavior and for infinite dimensional dynamical systems. So construction of impulsive systems, it's rather classical. So the impulsive dynamical system consists of three components. Yes, the classical or continuous dynamical system V, the impulsive set M, and impulsive map I. And to avoid some unpleasant behavior, like sticking on the M, we need some assumptions. The first one, that M intersect would be empty set. So if we jump into a new position which does not belong to M. The assumption 2 means that if we start from M, then at least on some time, the point V, T, X doesn't belong in direct time. So if we assume these properties, then we can prove that we can correctly define S of, this is the first moment. So you see, if M plus of X is non-empty set, then it means that trajectory starting from X impulsive effect. And these assumptions allows us to claim that this first moment of intersection is really positive. It's not clear in infinite dimensional situation. In finite dimensional situation, it's clear. So S of X is our first moment of meeting of our trajectory with impulsive set M. And then the construction is, so if we have no impulsive effects, that then our dynamical system V bar coincides with the continuous one. But if we have impulsive effect, so we construct V bar in the following way: V of Tx before jump and at the point of jump. And after that, we start again with this new position, and etc., etc., etc. As a result, we obtain finite or infinite number of impulsive points, x0 plus, x1 plus, x2 plus. Here is a new position, so the new jump points, and moment of time, Tn as a sum from k equals 0 to n of sk, the time interval process. And this formula, V bar Tx, defines our impulsive dynamic, yes. But we need that this map V bar as a function of t is defined on the whole axis from 0 to plus infinity. In the system, it can happen that we have beating effects. So the trajectory is so fast beat to impulsive set that this mapping V bar Tx can be not defined on the whole interval. So we assume that this is true. So we have no beating effect here, no Zeno effect, beating effect or Zeno effect. After that, no, it means that either the number of impulsive points are finite, or this series is convergent, or is equals infinity. Equals infinity. So if it's true, then our dynamical system, impulsive dynamical system, is defined. So this is the really semi-group, but not continuous. It's semi-group. As I said before, omega limit set for semi-groups are not invariant, in fact. So we have to replace the notion of invariance by something else. And I propose to replace the property of invariance by the property of minimality. So a compact, this is definition, this is the key definition of this presentation. So a compact set theta is called uniform attractor of dynamical system V bar if its attracting set and minimal among all closed uniformly attracting sets. This definition is borrowed from non-autonomous theory. Of course, if our dynamical system has classical global attractor theta bar, then this object coincides, no problem. For this uniform attractor, there exists very clear and simple criteria for existence. Assume that our dynamical system V bar is dissipative. Then V bar has uniform attractor if and only if it's asymptotically compact. So we need to, for existence, we need to verify two assumptions: the dissipativity and asymptotically compactness, and that's all. So let's, but it's not simple to guarantee the existence of such object in infinite dimensional case. Let's have a look at this simple example. So we have parabolic, linear parabolic system. Psi here and after is psi and lambda I will be the solution of this spectral problem. And of course, using the Fourier analysis, we can represent solution as a series of this form. And this dynamical system V, of course, is exponentially stable, exponentially fast. It tends to zero, so theta equals zero is a global attractor and attracts all trajectories exponentially fast. But if we consider these impulsive parameters, epsilon is arbitrarily small and mu is arbitrarily small, but positive. So if we consider M as a sphere of radius epsilon, and I is a map acting on the radius of arbitrarily small, then it can be proved that this problem generates impulsive dynamical system. No problem with that. Assumptions 1, 2, and 3 are satisfied, and the system, of course, is dissipative because it's trivial to show. But this impulsive dynamical system do not possess uniform attraction. So these small impulsive perturbations destroy uniform attraction. Here's a sketch of the proof. It's simple and based on the simple calculations, but so you see that this series tends to infinity. So here is a moment of intersection of meetings with the impulsive set Si. V is dissipative, and here is a dissipative set, but this impulsive system is not asymptotically compact. What is the problem? The problem is I can take these initial points y0 n, you see, epsilon mu plus 1 Cn, and this initial problem is bounded but not precompact. And for the moments tau n tends to infinity. So this is our asymptotic behavior. V bar tau n y0 n equals y0 n. So the limit behavior is not compact of this system because too many impulsive points. This set is bounded, but it's not compact. So this is, and this example also can show how to choose this impulsive map, this impulsive set N. So if the set is infinite dimensional, generally speaking, we cannot expect existence of uniform attractor in general. One way how to avoid this problem is to consider impulsive parameters which involve only finite coordinates of the phase vector. So let's P is some number, finite number, and M, our impulsive set, consists of points which involves or which consists of points which satisfy this equality. And you see that we involve only P first coordinates of the phase vector. And I, from M to M bar, our impulsive map, arbitrary impulsive map. It doesn't matter the precise value of I, but what is important that this I of Y involve finite coordinates of the phase vector. Oh, for example, this example is a simple example, so just a product of 1 plus mu of the coordinate of the phase vector. Here's the next examples, how it can be. This is the two coordinates, yes, and we increase only the first coordinate and stay the second coordinate without any changes, or we can add some numbers to the first coordinate and to the second coordinate, doesn't matter. So the key moment is the using of the finite number of coordinates. Then for linear case, again, it's a simple calculation based on the Fourier analysis. So we have the precise formula of solution, so no problem to calculate and to verify some properties. So for every P, if we consider these impulsive parameters, as I said, then our impulsive problem for parabolic linear case generates impulsive dynamical system V bar, which has uniform attractor theta, and we have precise formula for theta. It can be calculated. Then the theta has this particular form. Just remark that this theta is not invariant with respect to V bar. Of course, it's not connected. You see that we have union with zero, so the set is not connected. Of course, in impulsive dynamical system, we cannot expect connectedness. And theta is not invariant. But the problem is how to guarantee existence of uniform attractor if we face with nonlinear problem, if we have no precise formula for solution. So this is the existence theory. There is a sufficient conditions what we should do to be sure that our system has global attractor. So let's assume that our dynamical system V bar, our impulsive dynamical system V bar, which consists of continuous dynamical system V, impulsive set M, and impulsive map I, satisfy assumptions 1, 2, and 3. So it's necessary in any case. And also, you see these inequalities. Here is just an a priori estimates in the phase space for V, for continuous V. Here is an a priori estimates in the space continuously embedded in H. Of course, this theorem focuses on parabolic case. But for hyperbolic case, no problem to generalize these assumptions in standard way. So the next one is I. For I, our impulsive map must be bounded both in H and in Y. And the final assumption that the S of X, so the first moment of intersection with impulsive set, for trajectories starting from I of M must be positive, uniformly positive. If these assumptions hold, then we can guarantee that our impulsive dynamical system has uniform attraction. So this is a sufficient condition for this. And here's application. Here's application to nonlinear problem. We consider semi-linear, weakly semi-linear problem. So epsilon is a small parameter here. It's important. Unfortunately, I don't know how to verify really how to verify all these assumptions if we have non-small non-linearity. It's a difficult. But for small non-linearity, it's possible. So epsilon is a small parameter, F is continuous, H equals L2, our phase space, and M is the following impulsive set. I, arbitrary impulsive map, which involve only the finite numbers of the coordinates of the phase vector. Then it can be proved that for sufficiently small epsilon, we have no precise formula, of course, in this case, but for sufficiently small epsilon, this impulsive problem generates impulsive dynamical system B epsilon bar, and this dynamical system has uniform attractor theta epsilon, and theta epsilon tends to theta as epsilon tends to infinity. And theta is the uniform attractor of our linear system, which have a precise formula. The sketch of the proof. In fact, we have two difficulties. The first one, how to estimate these moments of intersection with impulsive set. And the main tool is implicit function theory. If we know everything for linear systems, so we have S0, epsilon equals 0, and S0 is our moment of intersection with impulsive set. And then near this point, we can apply implicit function theorem, considering these functions, which is built according to our impulsive parameters, and obtain this inequality 44 as epsilon minus S0 less or equal than K. K depends only on the parameter of the problem, multiplied by epsilon. So, and from this, I can derive the required properties for our system. It concerns existence of uniform attractor. About limit behavior, this is the rather huge formulas, but the main idea is the following. We need to prove, just a moment, we need to prove this limit equality as epsilon tends to 0. So, for this purpose, we goes to continuous, according to construction of our impulsive dynamical system, we goes to continuous dynamical system starting from our impulsive points eta k plus. Eta k plus, we can prove that it tends to some eta, tau k tends to some tau, but the problem is the following. We need to prove that this tail tends to 0 as k tends to infinity. And it can be proved because our impulsive action involves only finite number of parameters. So it can be proved that after coordinates, beginning from the coordinates p plus 1 and other coordinates, in this case tends to 0 case. Fourier coefficient tends to 0 as k tends to infinity. So, and I can prove the following, the required limit equality. And here I essentially use the precise formula for theta. So this is the sketch of the proof of this result. So let's speak about invariance. As I said before, the uniform attractor is not invariant in any sense. Here's the simple example. Again, linear problem. The very simple impulsive set M and impulsive map I. So we involve only the first coordinate from 1 to 1 plus mu after jump. The uniform attractor has the following form, very simple form, and by simple calculations we can show that no positive, no negative invariance. The problem is that the non-empty intersection of theta and the impulsive set M. And here is not my idea, is idea of Professor Bonotto, that the expected result is the following. We can expect that the non-impulsive part of uniform attractor becomes invariant. So is expected result. How to achieve this result? How to achieve this equality? For this purpose, we need this function, capital S of x. Here is S of x, so the first moment of intersection, if we have intersection, and plus infinity otherwise. So it's S of x is the moment of intersection with the impulsive set, or plus infinity if we have non-impulsive case. So our additional assumptions is the following. The map I should be continuous. It's not a problem at all, because I is a given map. And the assumption 5, for every xn tends to x, which does not belong to M, either S of x equals infinity if S of xn equals infinity for infinitely many n, or S of xn tends to S of x otherwise. Here I want to emphasize that for impulsive problems, the epsilon delta language is not a good tool, because in nonlinear PDEs, what we have? We have good theorems about limit transition, like Fatou lemma, Lebesgue's convergence dominated theorem, or compactness theorem, etc., etc., etc. So we should base it on limit on language like limit convergence sequence, not epsilon delta properties, but convergence sequence language. So, and all these properties can be verified with the help of limit transitions in particular problems. So the theorem is the following. If we assume that our dynamic impulsive dynamical system satisfies all these assumptions 1, 4, 2, 3, 4, and 5, and theta is a uniform attractor of V bar, then the non-impulsive part of attractor will be positively invariant. If additionally we assume that for every xn tends to x which belongs to M, either S of xn equals infinity or S of xn tends to 0 is a particular behavior near the limit set, of course, then the non-impulsive part of our attractor will be strictly invalid. Here's an application again for our semi-linear problem. The only additional assumption is that I should be continuous, and that's all. So under these additional assumptions, we can prove that for this problem generates dynamical system, impulsive dynamical system, which has uniform attractor theta epsilon, and the theta epsilon without M is invalid. The sketch of the proof, again, the proof is based on the on application of implicit function theory. And again, we use linear problem. So in all this consideration, the key moment is the small value of epsilon. So we have small non-linearity. So we have here the arguments by contradiction. So if we assume the problem is to just a moment. The problem is to verify the first line of assumption 5. The other assumptions is a consequence of limit transition theorem. No problem in nonlinear case. But the first line of assumption 5 is a real challenge, because it's not a limit transition. It's a little bit complicated. So we should prove that if xn tends to x, and if from xn the non-impulsive trajectory starts, then the same will be true for x. So we arguing by contradiction, we can prove it using implicit function theorem and using the results for linear system obtain the contradiction. So there is a tool how to do it. Assumption 5 is too restrictive. In fact, for example, for invariance is too restrictive, because if we, for example, this example, we consider this the trivial linear problem, exponentially stable, and M is the following set, and I, impulsive map, I of z equals 2 multiplied by z. So it acts along the ray. So here is our set M, and this is the ray. And if our trajectory meets M, it jumps into a new position on this line. So it's no problem by simple calculation to prove that this problem generates impulsive dynamical system with uniform attractor, and this attractor has the precise view, is this line. But and of course this the non-impulsive part of this uniform attractor is invariant. It can be calculated directly, but assumption 5 does not take place, because if I take the sequence that n tends to z, s of zn is infinity. So from that n is the initial point for non-impulsive trajectory, but s of z is finite. So that and assumption 5 doesn't take place. How to weaken this property? This example show the following fact. If we take Tn tends to infinity, but eventually we are interested in limit behavior of trajectory. So we're interested in behavior as t tends to infinity. So if we take Tn tends to infinity, we observe that v of Tn is Zn tends to 0, and s of 0 equals infinity. So the result is the following. The assumption 5, which is hard to verify for nonlinear case, can be replaced by the following one. For every xn tends to x, which does not belong to n, either s of xn equals infinity if s of xn equals infinity, tn tends to infinity, and xi is a limit of p of tn xn, then s of xi must be infinity. So in this case, or s of xn tends to s of x otherwise. So the assumption 5 can be replaced by the following one. And this assumption can easily be verified for nonlinear problems. What about stability? Very briefly, the stability, of course, is more sensitive property than invariance. And if we have no invariance, so we cannot expect stability. But let's have a look at this, again, simple example. Here is theta, uniform attractor for our linear impulsive problem. Everything okay. What about perturbation of impulsive set? So we just see that these problems are very sensitive to perturbations of impulsive parameters. In fact, if we perturb our impulsive set M by the following infinite dimensional sphere, here is M0 epsilon, here is this part of sphere, using, of course, again, we use infinite dimensionality of our problem. Psi n bigger than 2 and up to infinity. Then, of course, the Hausdorff distance between M and M epsilon is small. So this h between n, M epsilon and M tends to 0 is epsilon tends to 0. But we can prove that in this case, this small perturbation destroy uniform attractor. So this problem are very sensitive to perturbation of impulsive components. Now let's speak about stability with respect to flow. So stability in Lyapunov sense. Here is a classical equivalence between a couple of different notions of stability. So let A be a compact set, and the following property holds. So for xn tends to x belongs to A, and for every tn, the sequence V of tn xn must be precompact. Then the following stability conditions are equivalent. One is a classical stability. 2 and 3, just a reformulating of this property, but and the fourth one is the following: D plus of A is the following set. If theta is a uniform attractor of continuous dynamical system, then theta is stable in the sense of 1, 2, 3, and 4, no problem. But for the attractor theta of impulsive dynamical system, as well as for non-impulsive part of this theta, it's not true. It can easily be verified for linear case. So, but I want to emphasize that the 1, 2, and 3 definition of stability is given by the help of epsilon delta language, and the last one given by the help of convergence sequence language. So expected result is the following: that if we have invariance of theta minus m, so we can expect that d plus of theta minus m is a subset of theta minus m declosure. And this is a new definition of stability in the impulsive case. Of course, if we have continuous case, so it coincides with classical ones. And the following theorem guarantees these equalities. So if we suppose that assumption 1, 2, and 3, and additionally assumption 4 and assumption 5 take place, and theta is a uniform attractor of our impulsive dynamical system, then we have these equalities. The second one belongs to Professor Bonotto, but in these lines, so we obtain this, and we consider this equality as a structural property of uniform attractor. And the non-impulsive part of attractor is stable in this sense, so it can be proved. It can be proved. So conclusions. Final stage. Are the problems which can be considered from this point of view, and are the variants of impulsive sets, impulsive maps. It's not necessary the hyperplanes. It can be ellipsoids like that one, and here is the parabolic system, n-dimensional parabolic system. So, and for this impulsive problem, we can prove existence of uniform attractor with the properties described above. And here is the hyperbolic equation, semi-linear, weakly semi-linear hyperbolic equations. And here is M is given with the help of semi-norm LP on the phase space E, H01 product L2. And again, we can prove the existence of uniform attractor with invariant non-impulsive part. And here is the final results. It's not published yet. Here we have impulsive problem, which involves not finite, but all coordinates of the phase vector. And so if the Fourier coefficients of this perturbation lambda is sufficiently large, of course, they tend to zero as I tends to infinity, but at least one of them must be large. So if this equality takes place, A is a parameter in this, it is a sphere of radius A, our impulsive set. So if this inequality takes place, then we can prove that for sufficiently small epsilon, our impulsive problem generates impulsive dynamical system, which has uniform attractor. And even more, this attractor tends to attractor of linear problem as epsilon tends to 0. But this result is unproved yet, the last one, only in some particular cases. So that's all. Thank you for your attention, and stand with you.
Thank you, Professor Oleksiy. Let's thank Professor. So now we open to questions in the audience. Does anyone have a question? Please just open the microphone.
I have.
Okay, Professor Veraldo.
Okay.
Hi. Thank you for your talk. It was really nice. I would like to know some general condition about your assumption number 5. When you say that xn converges to x, or the impact function is infinite if the impact function of the sequence is infinite, or the impact function converges to the impact of x. Did you work in some general results to guarantee that conditions? Because in the
just a moment. Maybe I show the slide, and you
like that, the assumption
Yes,
5
yes,
or
this
assumption,
slide, yes.
yeah, like Chichelski have some tube condition. We did some
Yes,
condition.
yes.
Yeah.
I really don't need tube conditions. What you need, you use in your works.
Yeah, because the tube condition is really hard in infinite dimension
Yes,
space.
yes, it's.
We have done some other condition, like you call the condition T to avoid the tube conditions.
In fact, when I read your papers, I tried to verify tube conditions
Yeah.
for real nonlinear or weakly nonlinear infinite dimensional problem, and this is a real challenge. I don't know how to do it.
Yeah, it's difficult.
Because even for linear case, it can be done only for hyperbolic problem, because in hyperbolic case we have a group, not same group, but a group.
Yep.
In continuous case, so direct, so forward time, yes, and backward time. And for this problem, we can verify tube conditions, because tube condition says something about pre-image of the flow, yes?
Yep.
And this pre-image for negative time t, because we consider time after meeting and time before meeting, so we should consider negative t. I don't know really how to verify some properties for parabolic case, for example, for negative t.
Okay. But did you try to?
This is the most the aim of these assumptions, that it can be verified. Also, only for small epsilon. I really don't know how to verify these assumptions for serious nonlinear problems. It's just a small nonlinearity, just a toy, you know. It's just not a toy, but a test problem. For nonlinear case, I don't know really.
And the other question, because I also worked with some jump in the Fourier coefficient with a finite number. I don't know if you try to put impulse in an infinite number of coefficients. At this time, I didn't get something like that, because we got some trouble. When you put a number, a finite number in the jumps, it works well. But if you try to put a jump in an infinite number of the coefficients, something strange happens.
Yeah, something strange happened, and the only one idea is the only one idea which came in my mind is to consider if we have infinite dimensional sphere like this one, yes, infinite dimensional sphere, but consider the impulsive action not acting along the radius, because if impulsive action acting along the radius, we have no attractor, absolutely. But if we have just adding of some alpha, we can use Fourier analysis in some for small epsilon, like implicit function theorem, something like that. So, but by a simple calculation and estimation, we can estimate the main problem. You're right. The main problem, how to estimate the distance between impulses. This is the key idea, how to do it, and after that, this is it.
Okay.
So this is the problem. Of course, this is the problem, and up to now, only this result.
Okay, but thank you very much.
Thank you very much for your works.
Is there any other question? Well, if not, let's thank Professor Oleksiy Kapustyan again. Thank you, Professor, for the very nice talk. I'm sorry, Professor Alexander?
I just said very nice lecture.
Okay.
Thank you.
Thank you, Professor Carvalho. Thank you. I read also all your works.
We keep reading each other's work.
Yeah, I think so.
That's nice.
So thank you very much for invitation, and
Thank you.
it was a great